Hello, sleepy genius. The day has asked much of you, and now the night offers something in return: stillness, safety, and the gentle company of wonder. Let your shoulders drop, your breath slow, and your mind wander where it will. Tonight, you need only listen, and let the universe unfold its secrets, one discovery at a time. From clouds in space that smell like rum to planets made of diamond and stars so magnetic they could rip the iron out of your blood from miles away. We've found moons with subsurface oceans, rogue worlds drifting without a sun, and galaxies held together by something invisible we still can't identify. And just when we thought we understood gravity, space-time itself began to shake, revealing even deeper mysteries waiting in the dark. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please, share your thoughts below. Now, let's begin. Galileo discovered 4 moons orbiting Jupiter in January 1610. Using a telescope he had built himself. Picture a cold Italian night in Padua, Galileo squinting through ground glass at a bright point of light, watching as tiny stars seemed to dance around the giant planet, appearing and disappearing over successive nights. He called them the Mediterranean stars, hoping to flatter his patrons. But history would remember them as the Galilean moons: Io, Europa, Ganymede, and Callisto. This discovery shattered the ancient belief that all celestial bodies orbited Earth. Within weeks, Galileo had documented their movements, proving that at least some objects in the heavens circled something other than our world. To think that such a small instrument, barely stronger than modern binoculars, could overturn thousands of years of certainty. Saturn's rings were first observed by Galileo in 1610, though he could not understand what he was seeing. Imagine peering through primitive lenses at a pale yellow sphere that seemed to have handles, or perhaps ears, protruding from its sides. Galileo described Saturn as having companions that never moved or changed. His telescope was simply not powerful enough to resolve the true nature of these appendages. In 1655, Dutch astronomer Christian Huygens, using a superior telescope, recognized them as a flat ring surrounding the planet. He published his findings in Systema Saturnium, describing a thin, flat ring that nowhere touched the planet's surface. Giovanni Cassini later discovered a gap in the rings in 1675, now called the Cassini division. This reminds us that even genius has limits, and sometimes the truth must wait for better tools. Edmund Halley predicted the return of a comet in 1705, marking the first time anyone demonstrated that comets orbit the Sun. Consider the patience required. Halley studied historical records of bright comets from 1337, 1456, 1531, 1607, and 1682, noticing that they appeared at roughly 76-year intervals. He concluded they were all the same object, traveling in an elongated ellipse around our star. Halley calculated it would return in 1758, though he knew he would not live to see it. When the comet blazed into view on Christmas night 1758, exactly as predicted, it vindicated not only Halley but Newton's laws of motion. The comet has borne his name ever since, a gift from a man to the future. To think that mathematics could see across decades into a sky not yet darkened. William Herschel discovered Uranus on March 13, 1781, the first planet found since ancient times. Picture a cold night in Bath, England, Herschel conducting a systematic survey of the heavens with a homemade reflecting telescope in his garden. He noticed a pale greenish disk that moved against the background stars over successive nights. At first, he thought it a comet, but mathematicians soon calculated its orbit and confirmed it was a planet, nearly 2 billion miles from the Sun. Herschel wanted to name it Georgium Sidus, after King George III, but the astronomical community eventually settled on Uranus, continuing the tradition of Roman gods. The discovery doubled the known size of the solar system overnight. This reminds us that the universe holds wonders even in the spaces we thought we knew. The first asteroid, Ceres, was discovered by Giuseppe Piazzi on January 1, 1801, in Palermo, Sicily. Imagine beginning a new century by finding a new world, a faint point of light moving slowly through Taurus. Piazzi observed it for 24 nights before illness interrupted his work, and by the time he recovered, Ceres had moved too close to the Sun to observe. The mathematical prodigy Carl Friedrich Gauss, then only 24 years old, developed a new method of orbit calculation and predicted where Ceres would reappear. Astronomers found it exactly where Gauss said it would be in December 1801. Ceres orbits in the asteroid belt between Mars and Jupiter, a spherical body 590 miles in diameter, large enough that gravity has pulled it into a round shape. To think that mathematics could find a lost world in the vastness of space. Neptune was discovered through pure mathematics before it was ever seen. Picture two mathematicians, Urbain Le Verrier in Paris and John Couch Adams in Cambridge, independently calculating that irregularities in Uranus's orbit must be caused by an unknown planet's gravity. Le Verrier sent his predictions to Johann Galle at the Berlin Observatory in September 1846. That very night, Galle aimed his telescope at the coordinates and found Neptune within 1 degree of the predicted position, a pale blue disk 2.8 billion miles from the Sun. The planet had been observed before, even by Galileo in 1612, but always mistaken for a star. Adams had calculated its position months earlier, but British astronomers delayed their search. In a sense, Neptune is the greatest triumph of Newtonian physics. A world revealed not by light, but by invisible forces tugging on another world. The speed of light was first measured accurately by Léon Foucault in E-bar-Lioir, using rotating mirrors in his Paris laboratory. Imagine a beam of light bouncing between mirrors just 20 meters apart, the rotation blurring and shifting the reflection by tiny amounts. Foucault calculated that light traveled at 298,000 kilometers per second, remarkably close to the modern value of 299,792 kilometers per second. Earlier attempts by Hippolyte Fizeau in 1849 used a spinning-toothed wheel and gave similar results. Before these experiments, some scientists believed light traveled instantaneously. Al-Rachma had demonstrated in 1676 that light had finite speed by observing delays in Jupiter's moon eclipses, but he could not measure it precisely. This reminds us that even something as fundamental as the speed of existence itself remained mysterious until very recently in human history. The first spectroscopic analysis of starlight was performed by Joseph von Fraunhofer in 1814, revealing dark lines in the sun's spectrum. Picture sunlight passing through a prism, spreading into a rainbow crossed by hundreds of thin black lines, like a barcode written in shadow. Fraunhofer catalogued over 570 of these lines, assigning letters to the most prominent. He did not know what caused them, only that they were always in the same positions. Later, Gustav Kirchhoff and Robert Bunsen realized in 1859 that each chemical element absorbs specific wavelengths, creating its unique pattern of dark lines. This meant scientists could determine a star's composition from millions of miles away, simply by examining its light. Fraunhofer had unlocked stellar chemistry without leaving Earth. To think that light carries within it the signature of distant suns. The Doppler effect was described by Christian Doppler in 1842, explaining how motion changes the frequency of waves. Consider a train whistle that sounds higher as it approaches and lower as it recedes. The sound waves compressed ahead and stretched behind by the locomotive's motion. Doppler proposed that the same principle applied to light, meaning stars moving toward Earth would appear slightly bluer, and stars moving away would appear redder. Hippolyte Fizeau independently reached the same conclusion for light in 1848. This principle became crucial for measuring the motion of stars and, eventually, for discovering that the universe itself is expanding. In 1868, William Huggins used this technique to measure the radial velocity of Sirius, finding it was moving away from us at 29 kilometers per second. This reminds us that even standing still, we can measure the dance of distant suns. Helium was discovered in the Sun before it was found on Earth, through spectroscopy during a solar eclipse. Imagine the moon's shadow racing across India on August 18, 1868. As French astronomer Pierre Janssen observed the sun's chromosphere through a spectroscope, he saw a bright yellow line that did not match any known element. British astronomer Norman Lockyer observed the same line later that year and proposed it belonged to a new element, which he named helium after Helios, the Greek sun god. For 27 years, helium remained a purely celestial element until William Ramsay isolated it from uranium ore in 1895 by heating clavate. Helium is the second most abundant element in the universe, yet it hid from human knowledge until we studied sunlight. To think that a piece of the sun was named before it was ever held. The Great Red Spot of Jupiter was first observed by Robert Hooke in 1664, and it has been raging ever since. Picture a storm larger than Earth, a vast oval of churning clouds, colored rust red and cream, spinning counterclockwise in Jupiter's southern hemisphere. Giovanni Cassini made detailed observations in 1665, and the spot has been continuously monitored since 1830. The storm measures roughly 10,000 miles across today, though historical records suggest it was once much larger, perhaps 40,000 miles wide in the 1800s. Wind speeds at its edges reach 270 miles per hour. The red color likely comes from complex organic molecules and phosphorus compounds dredged up from deeper atmospheric layers and altered by ultraviolet sunlight. This reminds us that some cosmic phenomena outlive empires, persisting through centuries while we watch and wonder. The Titius-Bode law, formulated in 1766 by Johann Daniel Titius and popularized by Johann Elliot Bode, seemed to predict planetary distances with eerie accuracy. Imagine a simple mathematical formula. Take the sequence 0, 3, 6, 12, 24, and so on, add 4 to each, then divide by 10. The results roughly matched the distances of known planets from the Sun in astronomical units. When Uranus was discovered in 1781, it fit the pattern perfectly. This convinced astronomers that a planet must exist between Mars and Jupiter, leading to the discovery of Ceres in 1801. But Neptune, discovered in 1846, did not fit the law at all, and neither did Pluto. Modern science considers the Titius-Bode law a mathematical coincidence, not a fundamental principle. To think that the universe almost seemed to follow human arithmetic, then chose not to. The transit of Venus across the Sun's face was used to measure the distance to the Sun itself. Picture June 3, 1769, when astronomers scattered across the globe from Tahiti to Siberia to Norway, all timed Venus's passage across the solar disk. By measuring the subtle differences in timing from different locations on Earth, they could use parallax to calculate the astronomical unit. Captain James Cook led an expedition to Tahiti specifically for this purpose, and his observations, combined with dozens of others, gave an Earth-Sun distance of about 93 million miles, remarkably close to the true value of 92.96 million miles. The French astronomer Guillaume Le Gentil suffered perhaps the worst luck. He spent 8 years traveling to observe the 1761 and 1769 transits, but clouds blocked his view during both events. This reminds us that the cosmos keeps its appointments whether we can see them or not. William Herschel discovered infrared radiation in 1800 by accident, using a thermometer and a prism. Imagine sunlight spread into a rainbow on a table, Herschel placing thermometers in different colors to measure their temperatures. He noticed that a thermometer placed just beyond the red end of the visible spectrum, where no light appeared, registered an even higher temperature than those in the colored regions. He called this invisible radiation caloric rays, though it would later be named infrared. This was the first discovery of electromagnetic radiation beyond the visible spectrum, revealing that light was far more than human eyes could see. Herschel had found a kind of light that warms but does not illuminate. To think that the sun speaks in languages our eyes cannot hear. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, most no larger than a grain of sand. Consider the region from 2.2 to 3.2 astronomical units from the Sun, a vast toroidal cloud of debris that never coalesced into a planet. After Ceres was discovered in 1801, astronomers found Pallas in 1802, Juno in 1804, and Vesta in 1807. By the 1850s, dozens were known. Today, we have catalogued over 1 million asteroids larger than a kilometer. Despite their numbers, their total mass equals only about 4% of the Moon's mass. Jupiter's immense gravity prevented these fragments from ever gathering into a world, stirring them into colliding, fragmenting chaos. Most asteroids are carbonaceous, stony, or metallic, remnants of the solar system's violent birth. This reminds us that not all beginnings lead to completion, and the spaces between worlds hold their own broken stories. The parallax of stars was first measured by Friedrich Bessel in 1838, finally proving Earth orbits the Sun. Picture Bessel at the Kingsburg Observatory, meticulously measuring the position of the star 61 Cygni over an entire year. He detected a tiny shift of 0.31 for arcseconds as Earth moved from one side of its orbit to the other. Like holding your thumb at arm's length and closing each eye alternately to see it jump. This angular change allowed Bessel to calculate that 61 Cygni lies 10.3 light-years away, or about 64 trillion miles. Thomas Henderson and Friedrich Struve independently measured parallaxes for Alpha Centauri and Vega around the same time. The measurements were so small that they had eluded astronomers for centuries, requiring telescopes and techniques of extraordinary precision. To think that our planet's year-long journey is so small compared to cosmic distances that even nearby stars barely seem to move. The discovery of Neptune's moon Triton came just 17 days after Neptune itself was found. Imagine William Lassell at his private observatory in Liverpool in October 1846, examining the new planet through his 24-inch reflecting telescope. He spotted a faint point of light orbiting Neptune in a retrograde direction, moving opposite to the planet's rotation. Triton is the 7th largest moon in the solar system, measuring 1,680 miles in diameter, and it orbits Neptune in just under 6 days. Its retrograde orbit suggests it did not form alongside Neptune but was captured from the Kuiper belt, perhaps during a violent gravitational encounter billions of years ago. Surface temperatures on Triton reach -235 degrees Celsius, making it one of the coldest objects in the solar system. This reminds us that even newly discovered worlds arrive with companions, and that capture can be as powerful as creation. Solar flares were first observed by Richard Carrington on September 1, 1859, during the largest geomagnetic storm in recorded history. Picture Carrington in his private observatory in Redhill, England, projecting an image of the sun's surface onto a screen, sketching a large group of sunspots. Suddenly, two brilliant beads of white light appeared over the sunspots, intensifying for 5 minutes before fading. Within hours, telegraph systems worldwide went haywire, with operators receiving electric shocks and papers catching fire from induced currents. Auroras were seen as far south as the Caribbean, so bright in the Rocky Mountains that miners woke and began making breakfast, thinking it was dawn. The Carrington event released energy equivalent to 10 billion atomic bombs. To think that the sun's moods can reach across 93 million miles and set our machines ablaze. The rings of Saturn were proven to be made of countless small particles by James Clerk Maxwell in 1857, solving a puzzle that had vexed astronomers for 2 centuries. Imagine Maxwell working through mathematical equations, demonstrating that a solid ring would be gravitationally unstable and would tear itself apart, while a liquid ring would break into droplets. Only a ring composed of innumerable small bodies, each in its own orbit, could remain stable. The French Academy of Sciences had offered a prize for solving this problem, and Maxwell's essay won it. His work predicted that the rings consisted of particles ranging from dust grains to house-sized boulders, all orbiting Saturn independently. The Cassini spacecraft confirmed this in exquisite detail between 2004 and 2017, revealing the rings to be 99.9% water ice. This reminds us that sometimes mathematics sees structure where eyes see only light. Kirchhoff's laws of spectroscopy, formulated in 1859, established that every element produces unique spectral lines when heated. Picture Gustav Kirchhoff and Robert Bunsen in their Heidelberg laboratory, heating various substances in a flame and analyzing the light through a spectroscope. They discovered that sodium always produces 2 closely spaced yellow lines, while potassium creates violet lines. Each element has its own unmistakable signature. By comparing these laboratory spectra to Fraunhofer's solar absorption lines, Kirchhoff identified sodium, calcium, magnesium, iron, chromium, and nickel in the sun's atmosphere. This technique, called spectroscopy, transformed astronomy from measuring positions and motions to determining compositions and temperatures of distant objects. Within a decade, astronomers had analyzed the chemical makeup of stars thousands of light years away. To think that fire and prisms gave us the keys to stellar chemistry. Mars's 2 small moons, Phobos and Deimos, were discovered by Asaph Hall in August 1877 during a particularly close approach of the red planet. Imagine Hall at the Naval Observatory in Washington, D.C., using the 26-inch refractor telescope, nearly giving up his search when his wife urged him to try one more night. On August 12th, he spotted Deimos, and on August 18th, he found Phobos, both captured as faint points of light crawling around Mars. Phobos orbits just 3,700 miles above Mars's surface, completing 3 orbits every Martian day, and it is slowly spiraling inward, destined to crash into Mars or break apart into a ring system within 50 million years. Deimos orbits farther out and will eventually escape into space. Both moons are irregularly shaped, likely captured asteroids, measuring just 17 and 9 miles across. This reminds us that even worlds have expiration dates. The spectrum of hydrogen was explained by Johann Balmer in 1885, revealing a mathematical pattern in its wavelengths. Picture Balmer, a 60-year-old Swiss schoolteacher with no formal training in physics, examining the 4 visible lines in hydrogen's spectrum: red, blue-green, blue, and violet. He discovered a simple formula that precisely predicted their wavelengths. Each line's wavelength could be calculated from whole numbers in the sequence 3, 4, 5, and 6. His formula was purely empirical. He had no idea why it worked. Later, Niels Bohr's quantum model of the atom in 1913 explained that these lines corresponded to electrons jumping between specific energy levels. The Balmer series became the first evidence that atoms have quantized energy states. To think that a pattern noticed by a teacher would help unlock the quantum nature of reality. The Gegenschein, or counterglow, is a faint brightening of the night sky exactly opposite the sun's position. Imagine standing under a perfectly dark sky, looking at the point on the celestial sphere directly away from the sun below your horizon. In that spot, slightly brighter than the surrounding darkness, glows a subtle oval patch about 10 degrees wide. Danish astronomer Theodor Brorsen described it in 1854, though earlier observers had noted it. The glow comes from sunlight backscattered off dust particles in the plane of the solar system, roughly at the distance of Mars's orbit. It is a cosmic opposition effect, the same phenomenon that makes your shadow's head appear to glow when the sun is directly behind you. Few people ever see the Gegenschein because light pollution drowns it, but it is always there. This reminds us that even Earth's shadow has a halo. The canals of Mars were reported by Giovanni Schiaparelli in 1877, sparking decades of speculation about Martian civilization. Picture Schiaparelli at the Brera Observatory in Milan, observing Mars through clear Italian nights and sketching straight lines crisscrossing the planet's surface. He called them canali, meaning channels in Italian, but the word was mistranslated as canals, implying artificial construction. Percival Lowell built an entire observatory in Flagstaff, Arizona, dedicated to studying these features, publishing maps showing hundreds of canals connecting dark regions he thought were seas. Lowell believed an advanced but dying Martian civilization had built a planet-wide irrigation system to transport water from polar ice caps. Better telescopes eventually revealed no such features existed. They were optical illusions created by the eye's tendency to connect random features into lines. To think that our longing for cosmic companions could sketch entire civilizations from shadows. The first photograph of a stellar spectrum was taken by Henry Draper in 1872, capturing the spectrum of Vega. Imagine the patience required to expose a wet collodion plate to starlight gathered through a telescope and spread through a prism, holding everything steady for minutes, while the faint rainbow of Vega's light chemically etched itself onto glass. Draper's photograph showed the dark absorption lines that Fraunhofer had seen visually, but now they could be measured precisely and studied at leisure. Draper went on to photograph spectra of many bright stars before his death in 1882. His widow funded a massive ictroscopic survey of stars at Harvard College Observatory, resulting in the Henry Draper Catalogue, which classified over 225,000 stars by their spectra. This reminds us that sometimes the best way to study light is to trap it, to freeze its message in silver. Annie Jump Cannon developed the stellar classification system still used today, organizing stars by temperature. Picture Cannon at Harvard College Observatory in the early 1900s. examining thousands upon thousands of photographic spectra, looking for patterns in the dark lines. She streamlined the existing chaotic system into a simple sequence, OBAFGKM, from hottest to coolest, running from blue-white stars over 30,000 Kelvin to red stars under 3,500 Kelvin. Astronomy students still remember the sequence with the mnemonic "Obia Fine Girl, Kiss Me." Cannon personally classified over 350,000 stars in her career, more than anyone else in history. Her work revealed that stars form a continuous sequence of types, not separate categories. To think that one woman's pattern recognition organized the entire population of visible stars. The discovery of helium on Earth in 1895 by William Ramsay came from a peculiar source, uranium, or Imagine Ramsay in his London laboratory, heating a sample of clavet, a uranium-bearing mineral from Norway, and analyzing the gas released. When he examined the gas's spectrum, he saw the same yellow line that had puzzled astronomers observing the Sun 27 years earlier. Helium had finally been found on Earth, trapped in radioactive minerals by alpha decay, which produces helium nuclei. Ramsay had already discovered argon the previous year, and he would go on to discover neon, krypton, and xenon, adding an entire column to the periodic table. Helium's presence in uranium ore revealed a connection between radioactivity and transmutation that would revolutionize physics. This reminds us that sometimes celestial mysteries are solved in basement laboratories, not observatories. The Perseid meteor shower occurs every August when Earth passes through debris left by comet Swift-Tugtal. Picture a warm summer night, lying on your back watching dozens of bright streaks per hour radiate from the constellation Perseus. Giovanni Schiaparelli realized in 1866 that meteor showers occurred when Earth crossed the orbits of comets, encountering streams of dust and small rocks left in the comet's wake. The Perseids are fragments shed by Swift-Tugtal during its 133-year orbit around the Sun. Each particle, most no larger than a grain of sand, enters our atmosphere at 37 miles per second, heating the air around it to thousands of degrees and creating the brilliant streak we call a shooting star. The meteor itself rarely reaches the ground. We are seeing heated air, not the particle itself. To think that wishes are made on comet dust burning up miles above our heads. The Leonid meteor storm of 1833 was so intense that an estimated 100,000 meteors per hour filled the sky over North America. Imagine waking before dawn on November 13, 1833, to see the entire sky ablaze with shooting stars, streaking in all directions like a snowstorm of light. Many people thought the world was ending. Denison Olmsted at Yale College collected eyewitness accounts and realized that all the meteors appeared to radiate from the constellation Leo, proving they were an astronomical phenomenon, not atmospheric. This event sparked serious scientific study of meteor showers. The Leonid storm, roughly every 33 years, when Earth passes through particularly dense debris from comet Tempest-Tugtal, the 1966 Leonid storm over the southwestern United States peaked at an estimated 150,000 meteors per hour. This reminds us that the sky occasionally performs shows that humble fireworks into insignificance. The first asteroid discovered in the 20th century was Eros, found by Gustav Witt in 1898, and it became significant for measuring the solar system. Imagine an asteroid that occasionally passes within 14 million miles of Earth, close enough that its parallax could be measured accurately from different observing stations worldwide. During Eros's close approach in 1930-1931, astronomers at observatories around the globe carefully measured its position, using the parallax to refine the scale of the solar system. These observations, combined with advanced calculations, yielded a solar parallax of 8.790 arcseconds, corresponding to an Earth-Sun distance of 92.9 million miles. Eros is an elongated body about 20 miles long, tumbling end over end every 5.27 hours. In 2000, the near-Shoemaker spacecraft became the first probe to orbit and land on an asteroid when it set down on Eros. To think that a small rock could serve as a measuring rod for the scale of everything. The tail of a comet always points away from the sun, not in the direction of its motion. Picture a comet swooping around the sun on its elliptical path, its tail streaming not behind it like a pennant on a speeding train, but pushed outward by the solar wind and radiation pressure. Johannes Kepler noticed this in 1619, proposing that sunlight exerted a force on the comet's material. Friedrich Bessel confirmed this in 1835 while observing Halley's comet, showing that comets often have two tails, a straight, bluish ion tail blown by the solar wind, and a curved, yellowish dust tail pushed by radiation pressure. The ion tail can extend for hundreds of millions of miles, while the dust tail is typically shorter and follows the comet's orbital curve. To think that the sun's breath shapes even objects millions of miles away, turning inward-falling ice into outward-flowing beauty. The Crab Nebula was connected to a historical supernova explosion recorded in 1054 by Chinese astronomers. Picture the night of July 4th, 1054, when Chinese court astronomers observed a new star in Taurus, so bright it was visible in daylight for 23 days and remained visible at night for 653 days. They called it a guest star, meticulously recording its position and duration. In 1731, John Bevis catalogued a fuzzy patch in the same location, and Charles Messier observed it in 1758 while comet hunting, listing it as M1, the first entry in his famous catalogue. In 1921, John Duncan at Mount Wilson Observatory noticed the nebula was expanding, and calculations backward in time placed its origin around 1054. The nebula is now 11 light-years across and expanding at 930 miles per second, powered by a pulsar spinning 30 times per second at its heart. To think that medieval astronomers witnessed the death scream of a star 6,500 light-years away. Pluto was discovered by Clyde Tombaugh on February 18, 1930, after a systematic photographic search of the sky. Imagine a 24-year-old farm boy from Kansas, hired by Lowell Observatory, spending hours comparing photographic plates taken days apart, looking for objects that moved against the background stars. Using a device called a blink comparator that rapidly switched between two images, Tombaugh examined millions of star images. Near the predicted position calculated by Percival Lowell, he found a 15th magnitude object that had shifted between the plates. Pluto orbits the Sun every 248 years at an average distance of 3.7 billion miles. Its elliptical path sometimes bringing it closer than Neptune. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet after discovering it was merely one of many similar objects in the Kuiper Belt. This reminds us that categories matter less than what we learn, and demotion does not diminish wonder. Henrietta Swan Leavitt discovered the period luminosity relationship of Cepheid variable stars in 1912, giving astronomy its first cosmic measuring stick. Picture Leavitt at Harvard College Observatory, examining thousands of photographic plates of the Small Magellanic Cloud, a satellite galaxy of the Milky Way. she noticed that brighter Cepheid variables took longer to complete their brightness cycles, ranging from days to months. Because all stars in the Small Magellanic Cloud are roughly the same distance from Earth, this meant their actual luminosities were related to their periods. By measuring a Cepheid's period, astronomers could calculate its true brightness, and by comparing that to its apparent brightness, determine its distance. Edwin Hubble would later use this technique to prove that spiral nebulae were separate galaxies millions of light-years away. To think that a pattern in pulsing stars became the ruler for measuring the universe. Einstein's general theory of relativity was confirmed during the solar eclipse of May 29, 1919, when starlight was observed bending around the Sun. Picture two expeditions, one led by Arthur Eddington to Principe Island off Africa, another to Sobral, Brazil, both photographing stars near the Sun's edge during totality. Einstein had predicted that the Sun's gravity would curve space-time itself, deflecting light from distant stars by 1.75 arcseconds as it passed near the solar limb. Without an eclipse, the Sun's glare makes these stars invisible. But during the few minutes of totality, they could be photographed and compared to images taken when the Sun was elsewhere. Eddington's measurements showed deflection of 1.61 arcseconds, close enough to confirm Einstein's prediction over Newton's 0.87 arcseconds. The announcement in November 1919 made Einstein instantly famous worldwide. This reminds us that light does not travel in straight lines through the cosmos. It follows the curves that mass carves into the fabric of space itself. The existence of dark nebulae was established by Edward Emerson Barnard through photography in the early 1900s. Imagine pointing a camera at the Milky Way and seeing vast, dark patches where no stars shine, not because no stars exist there, but because clouds of dust block their light. Barnard catalogued 349 of these dark nebulae, including the famous Horsehead Nebula in Orion and the Coalsack near the Southern Cross. Some astronomers thought these were simply regions without stars, holes in the celestial sphere, but Barnard argued they were clouds of obscuring matter. His photographs showed dark nebulae outlined against bright emission nebulae behind them. These clouds consist of gas and dust so dense they block optical light completely, though infrared telescopes can peer through them. Inside these dark wombs, hidden from visible light, new stars are being born. To think that darkness in the sky sometimes means presence, not absence. Cecilia Pangaposhkin discovered in 1925 that stars are primarily composed of hydrogen and helium, overturning the assumption that stars had similar composition to Earth. Picture Payne analyzing stellar spectra for her doctoral thesis at Radcliffe College, applying new quantum physics to interpret absorption lines. She calculated that hydrogen was millions of times more abundant in stellar atmospheres than previously believed, with helium also vastly more common than heavier elements. Her thesis examiner, Henry Norris Russell, initially convinced her to soften her conclusion because it contradicted established wisdom. 4 years later, Russell confirmed her results and published them, often receiving credit for the discovery. Payne's work revealed that the universe is overwhelmingly made of the two lightest elements, with everything else being cosmic trace impurities. To think that we are made from the rare ingredients, the exotic spices in a cosmos of simple gases. The expanding universe was discovered by Edwin Hubble in 1929 through observations of distant galaxies. Imagine Hubble at Mount Wilson Observatory using the 100-inch Hooker telescope to measure the spectra and distances of dozens of galaxies. He found that nearly every galaxy showed redshifted spectral lines, meaning they were moving away from us. and the farther away a galaxy was, the faster it receded. A galaxy twice as distant was moving away twice as fast, a relationship now called Hubble's law. This discovery implied that the universe itself was expanding, with space growing between galaxies like raisins in rising bread dough. Hubble's original value for the expansion rate, now called the Hubble constant, was about 500 kilometers per second per megaparsec. Much too high, but the principle was correct. This reminds us that we live not in a static cosmos, but in an outward explosion still unfolding from ancient beginnings. Carl Jansky discovered radio waves from the Milky Way in 1931 while investigating static interference for Bell Telephone Laboratories. Picture Jansky in rural New Jersey, working with a large rotating antenna designed to track down sources of noise affecting transatlantic radio communications. He identified 3 types of static: nearby thunderstorms, distant thunderstorms, and a persistent hiss that rose and fell with a period of 23 hours and 56 minutes, the length of a sidereal day. This meant the source was celestial, and by tracking it across the sky, Jansky determined it came from the direction of Sagittarius, toward the center of our galaxy. He had discovered radio astronomy, revealing that the universe broadcasts not just in visible light, but across the entire electromagnetic spectrum. Despite this revolutionary finding, Bell Labs did not pursue it further, and Jansky never worked in astronomy again. To think that cosmic whispers were first heard not by astronomers, but by an engineer hunting telephone noise. Subramanian Chandrasekhar calculated in 1930 that white dwarf stars have a maximum mass limit of about 1.4 solar masses. Imagine Chandrasekhar as a 19-year-old student sailing from India to England for graduate studies, working through equations on the voyage and realizing that quantum mechanics and relativity combined to predict something startling. A white dwarf is held up against gravitational collapse by electron degeneracy pressure, but if the star exceeds this limit, now called the Chandrasekhar limit, no force can prevent further collapse. The star must become something else, a neutron star or black hole. When Chandrasekhar presented this work to the Royal Astronomical Society in 1935, Arthur Eddington publicly ridiculed it, believing no such collapse could occur. Decades later, the discovery of neutron stars and black holes vindicated Chandrasekhar completely. He received the Nobel Prize in 1983. This reminds us that math sometimes sees futures that intuition rejects. Fritz Zwicky discovered in 1933 that galaxy clusters contain dark matter by studying the Coma cluster. Picture Zwicky measuring the velocities of galaxies in the Coma cluster, finding they were moving far too fast to be held together by the visible matter's gravity. Applying the virial theorem, he calculated that the cluster must contain 400 times more mass than could be seen through telescopes. He called this unseen substance Dunkel Materie, dark matter. Zwicky also predicted the existence of neutron stars that same year and coined the term supernova to distinguish the brightest stellar explosions from ordinary novae. His colleagues often dismissed him as eccentric, but almost every one of his radical ideas was eventually confirmed. The Coma cluster, 320 million light-years away, does indeed contain vast quantities of invisible matter making up 90% of its mass. To think that most of the universe's matter neither emits nor reflects light, that we swim in an ocean of the unseen. Neutron stars were theorized by Walter Bod and Fritz Zwicky in 1934, just 1 year after the neutron itself was discovered. Imagine proposing that when massive stars explode as supernova, their cores collapse into spheres just 12 miles across but containing more mass than the Sun. where matter is compressed to nuclear density. A teaspoon of neutron star material would weigh 1 billion tons on Earth. Bod and Zwicky suggested that such objects would be the remnants of supernova explosions, held up against further collapse by neutron degeneracy pressure. The idea seemed too extreme for most astronomers, and neutron stars remained theoretical for 33 years. In 1967, Jocelyn Bell Burnell detected the first pulsar, a rapidly spinning neutron star emitting beams of radio waves like a lighthouse. To think that the densest possible matter that isn't a black hole spins hundreds of times per second. A collapsed sun, small enough to fit inside a city. The Great Red Spot of Jupiter was measured to have wind speeds of 270 miles per hour through spectroscopic observations in the 1960s. Consider a storm 3 times the diameter of Earth, where hurricane-force winds have blown continuously for at least 350 years, and possibly much longer. Observations by Giovanni Cassini in the 1660s may have been the same storm, though records are uncertain. The spot rotates counterclockwise every 6 days, driven by Jupiter's internal heat and rapid rotation. Its red color comes from complex organic compounds, likely phosphorus and sulfur, that are brought up from deeper in the atmosphere and altered by solar ultraviolet light. Recent observations from the Juno spacecraft show the storm extends about 200 miles deep into Jupiter's atmosphere. The spot has been shrinking since the 1800s, raising questions about whether it will disappear entirely within decades or reach some stable minimum size. This reminds us that even ancient storms must eventually fade, though their lifespans dwarf human civilizations. Venus rotates backward compared to most planets, spinning east to west rather than west to east. Picture a world that takes 243 Earth days to complete one rotation but only 225 Earth days to orbit the Sun, meaning a Venusian day is longer than its year. Moreover, Venus spins clockwise when viewed from above the solar system's north pole, opposite to its orbital direction and to the rotation of most other planets. This retrograde rotation likely resulted from a catastrophic collision early in the solar system's history, when a massive impact knocked Venus spinning in the opposite direction. The planet's thick atmosphere, 90 times denser than Earth's and composed of 96% carbon dioxide, creates surface temperatures of 465 degrees Celsius, hot enough to melt lead. Soviet Venera landers in the 1970s survived only minutes on the surface before being crushed and cooked. To think that our sister planet spins backward beneath crushing heat, a reminder that proximity does not guarantee similarity. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system. Imagine a world where hundreds of volcanoes constantly erupt, some shooting plumes of sulfur dioxide 250 miles into space, where the surface is continuously renewed by lava flows and has no impact craters because they are erased faster than they form. Voyager 1 captured the first images of Io's volcanoes in March 1979, with navigation engineer Linda Morabito discovering the first active extraterrestrial volcano in a processed image. Io's volcanism is powered by tidal heating, Jupiter's enormous gravity, along with gravitational tugs from Europa and Ganymede, constantly flexes Io's interior, generating friction and heat. The moon's surface is painted in yellows, oranges, reds, and blacks from sulfur and sulfur dioxide frost. Io radiates twice as much heat as it receives from the sun. This reminds us that moons can be as dynamic as planets, that gravity can be a forge. Europa, Jupiter's fourth largest moon, likely harbors a liquid water ocean beneath its icy crust. Picture a world slightly smaller than Earth's moon, covered in smooth ice crisscrossed by brown linear features called linear, where tidal heating from Jupiter keeps an ocean of liquid water perhaps 60 miles deep beneath a crust of ice 10 to 15 miles thick. The Galileo spacecraft's magnetometer detected a magnetic field consistent with a salty, electrically conductive ocean in the 1990s. Europa's surface is geologically young, only 40 to 90 million years old, constantly refreshed by ice upwelling from below. Dark material in the cracks appears to be salts and sulfur compounds from the subsurface ocean. If life exists in Europa's ocean, it would thrive in complete darkness, perhaps clustered around hydrothermal vents on the ocean floor, similar to life in Earth's deep oceans. To think that an alien sea, twice the volume of Earth's oceans, sloshes in darkness beneath eternal ice. The cosmic microwave background radiation was discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs. Imagine two radio astronomers calibrating a sensitive horn antenna for satellite communications. Troubled by persistent background noise coming equally from all directions, they cleaned out pigeon droppings, checked every connection, but the hiss remained, equivalent to a temperature of 3.5 Kelvin. Meanwhile, just miles away at Princeton, Robert Dick's team was building equipment to search for the predicted afterglow of the Big Bang. When the two groups learned of each other's work, they realized Penzias and Wilson had found exactly what Dick was looking for: the cooled remnant of the universe's fiery beginning, now stretched into microwaves by 13.8 billion years of cosmic expansion. This discovery provided the strongest evidence for the Big Bang theory and earned Penzias and Wilson the 1978 Nobel Prize. To think that creation's echo fills empty space, a whisper from when the universe first became transparent to light. Pulsars were discovered by Jocelyn Bell Burnell in July 1967 while analyzing radio telescope data from the Mullard Radio Astronomy Observatory. Picture Bell Burnell noticing a bit of scruff, a small signal, repeating with astonishing precision every 1.337 seconds in data from the constellation Vulpecula. She and her advisor Anthony Hewish initially joked it might be a signal from little green men, but soon found 3 more pulsating sources in other parts of the sky. Thomas Gold correctly interpreted them as rapidly rotating neutron stars with intense magnetic fields, beaming radio waves from their magnetic poles like lighthouses. The fastest known pulsar, discovered in 2006, spins 716 times per second, a star 20 miles across rotating faster than a kitchen blender. Pulsars slow down gradually as they radiate energy, and their timing is so precise they rival atomic clocks. To think that collapsed stars can spin hundreds of times each second, that remnants of stellar death become cosmic timepieces. The first black hole candidate, Cygnus X1, was identified in 1972 through X-ray observations and orbital analysis. Imagine a blue supergiant star orbiting an invisible companion every 5.6 days. The companion's gravity pulling streams of gas from the supergiant's outer layers, heating the infalling matter to millions of degrees until it screams in X-rays. The Uhuru X-ray satellite detected the intense X-ray source, and optical telescopes identified the blue supergiant HDE 226,868. By measuring the star's orbital motion, astronomers calculated the invisible companion must have at least 15 solar masses, far exceeding the maximum mass for neutron stars. The only possibility remaining was a black hole, a region where gravity is so intense that not even light can escape. Stephen Hawking famously bet Kip Thorne in 1975 that Cygnus X1 was not a black hole, but conceded in 1990. This reminds us that sometimes we see objects only by what they do to their surroundings. That absence can be more revealing than presence. Saturn's moon Titan was found to have a thick atmosphere in 1944 by Gerard Kuiper, the only moon in the solar system with a substantial atmosphere. Picture Kuiper at McDonald Observatory in Texas, using spectroscopy to detect methane absorption lines in light. Reflected from Titan, the atmosphere turned out to be 1.5 times denser than Earth's at sea level, composed of 95% nitrogen and 5% methane with traces of hydrogen, cyanide, and other organic compounds. The Cassini-Huygens mission revealed in 2005 that Titan has lakes and seas of liquid methane and ethane near its poles, river valleys carved by liquid hydrocarbons, and a hydrocarbon cycle analogous to Earth's water cycle. Titan's surface temperature of -179 degrees Celsius makes water ice as hard as rock, while methane plays the role water plays on Earth. To think that another world has weather and seasons and shorelines, though made of entirely different substances. Comet Shoemaker-Levy 9 collided with Jupiter in July 1994. The first observed collision between two solar system objects. Picture a comet torn into at least 21 fragments by Jupiter's tidal forces during a close pass in 1992. The fragments strung out like pearls on a string, each destined to slam into Jupiter 2 years later. Astronomers worldwide trained every available telescope on Jupiter as the fragments impacted over 6 days, each collision releasing energy equivalent to millions of megatons of TNT, creating dark scars in Jupiter's atmosphere larger than Earth that persisted for months. The largest fragment, Fragment G, created a fireball that rose 1,900 miles above Jupiter's cloud tops. The impacts occurred on Jupiter's far side, but the planet's rapid rotation brought the impact sites into view within minutes. To think that we witnessed cosmic violence on such scale, that Jupiter's gravity shields the inner solar system by capturing or deflecting countless objects that might otherwise strike Earth. The Kuiper belt was confirmed in 1992 with the discovery of 1992 QB1 by David Jewett and Jane Luo. Imagine searching for 5 years, taking hundreds of photographic plates of the outer solar system, looking for faint, slowly moving objects beyond Neptune. Gerard Kuiper had predicted in 1951 that a belt of icy bodies should exist beyond Neptune, remnants from the solar system's formation. Jewett and Louis found QB1, a 100-mile-wide object orbiting 41 astronomical units from the Sun, proving Kuiper's prediction correct. Thousands of Kuiper belt objects have since been discovered, including Pluto, now understood to be merely one of the largest members of this population. The belt extends from Neptune's orbit at 30 astronomical units to approximately 50 astronomical units. A vast reservoir of frozen worlds containing perhaps hundreds of millions of objects. To think that the solar system does not end with planets, but continues outward into a disk of ancient ice. The first exoplanet orbiting a sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz around the star 51 Pegasi. Picture Mayor and Queloz at the Haute-Provence Observatory in France, using the radial velocity method to detect the gravitational wobble the planet induced in its parent star. The planet, designated 51 Pegasi b, was utterly unexpected. A gas giant, at least half the mass of Jupiter, but orbiting its star every 4.2 days at a distance of just 5 million miles. Such hot Jupiters contradicted all theories of planetary formation, which held that gas giants should form only in the cold outer regions of stellar systems. The discovery opened the floodgates, and within 2 decades, astronomers had confirmed thousands of exoplanets orbiting other stars. Mayer and Queloz received the 2019 Nobel Prize in Physics. This reminds us that planets are not unique to our Sun, that worlds orbit every star we see. The Galileo spacecraft discovered evidence of a subsurface ocean on Jupiter's moon, Ganymede, in the 1990s through magnetic field measurements. Imagine a moon larger than Mercury, the 9th largest object in the solar system, possessing its own magnetic field generated by a liquid iron core, and beneath its icy crust, a saltwater ocean perhaps 60 miles deep. Ganymede's surface shows 2 distinct terrain types: dark, heavily cratered regions billions of years old, and younger, lighter grooved terrain where parallel ridges and valleys cover vast areas. The grooved terrain likely formed from tectonic activity driven by tidal heating, though far less intense than on Io or Europa. Recent observations suggest Ganymede's ocean may be sandwiched between layers of ice in different phases, with high-pressure ice forms on the ocean floor. To think that 3 of Jupiter's 4 largest moons hide oceans, that liquid water may be common in the outer solar system. Dark energy was discovered in 1998 through observations of distant supernova by 2 independent teams. Picture astronomers studying Type Ia supernova, stellar explosions that always reach the same peak brightness, making them perfect standard candles for measuring cosmic distances. Both teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, found that distant supernovae were fainter than expected, meaning they were farther away than predicted by a universe expanding at a constant rate. The universe's expansion was not slowing under gravity's pull, as everyone assumed, but accelerating, driven by some unknown energy filling empty space. This dark energy comprises about 68% of the universe's total energy density. Its nature remains mysterious, possibly a cosmological constant as Einstein once proposed, or perhaps something more complex. To think that the universe's fate is dominated by an invisible force pushing galaxies apart ever faster. Water ice was confirmed at the Moon's poles by the Lunar Prospector mission in 1998 through neutron spectrometry. Imagine permanently shadowed craters near the lunar poles where sunlight has not reached for billions of years, temperatures hovering at -240 degrees Celsius, cold enough that water ice can survive indefinitely. The neutron spectrometer detected hydrogen-rich regions in these shadows, consistent with water ice mixed into the lunar regolith. Later missions, including India's Chandrayaan-1 and NASA's LCROSS impact mission in 2009, confirmed the presence of water molecules and ice. The water likely came from comet impacts and solar wind hydrogen interacting with oxygen in lunar rocks. Some polar craters may contain hundreds of millions of tons of ice, a potential resource for future lunar bases. To think that the airless ancient moon has been quietly storing water in its darkest corners, hidden from the sun for eons. The first brown dwarf was confirmed in 1995 with the discovery of Gliese 229b by researchers using the Palomar Observatory. Picture an object more massive than any planet, but not massive enough to sustain hydrogen fusion in its core, occupying the gap between the heaviest planets and the lightest stars. Gliese 229b has about 20 to 50 times Jupiter's mass, orbiting a red dwarf star 19 light-years from Earth. Brown dwarfs glow dimly from residual heat from their formation and from deuterium fusion, which can occur at lower masses than hydrogen fusion. Their surface temperatures range from 250 to 2500 Kelvin, making them invisible to optical telescopes but detectable in infrared. Thousands of brown dwarfs have since been discovered, some floating freely through space without any parent star. To think that the line between planet and star is not sharp but blurred, that failed stars wander the galaxy in dim obscurity. The accelerating expansion of the universe earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Consider that for 13.8 billion years after the Big Bang, gravity from matter and dark matter had been slowing the universe's expansion. But about 5 billion years ago, the density of matter had decreased enough that dark energy's repulsive effect became dominant. Now the expansion accelerates, and if dark energy remains constant, galaxies outside our local group will eventually recede faster than light can travel toward us. In hundreds of billions of years, distant galaxies will disappear beyond our cosmic horizon, and astronomers in that far future will observe a universe apparently containing only their own galaxy. All evidence of the Big Bang and cosmic expansion erased. To think that we live in a brief cosmic era when the universe's history is still visible, that future astronomers may never know what we have learned. Enceladus, Saturn's sixth largest moon, was found to have active geysers erupting from its south pole in 2005. Picture the Cassini spacecraft, flying through plumes of water, vapor, and ice crystals, shooting 300 miles into space from 4 parallel cracks in Enceladus's icy crust. Features nicknamed tiger stripes. Analysis of the plume material revealed water vapor, ice particles, salts, silica, and simple organic compounds, indicating a liquid water ocean beneath the ice heated by tidal flexing from Saturn's gravity. The ocean is global, about 6 miles deep, sandwiched between the icy crust and a rocky core. The discovery made Enceladus one of the most promising places in the solar system to search for extraterrestrial life. The geysers supply material to Saturn's E-ring, making it the only ring constantly replenished by an active moon. To think that a tiny moon just 310 miles across harbors an ocean that openly advertises its presence by spraying water into space. The Higgs boson was discovered at CERN's Large Hadron Collider on July 4, 2012, confirming the final piece of the standard model of particle physics. Imagine 2 beams of protons accelerated to 99.99999% the speed of light, circulating in opposite directions through a 17-mile ring beneath the border of France and Switzerland, colliding head-on 600 million times per second. Among the debris of these collisions, physicists found evidence of a new particle with a mass of 125 GeV, matching predictions for the Higgs boson. This particle is associated with the Higgs field, a quantum field permeating all space that gives other particles their mass through interaction. Without the Higgs field, electrons, quarks, and other particles would be massless and would zip around at light speed, unable to form atoms. Peter Higgs and Francois Inglet, who had predicted the particle's existence in 1964, received the Nobel Prize in 2013. To think that mass itself arises from interaction with an invisible field filling the universe. Gravitational waves were directly detected for the first time on September 14, 2015, by LIGO, the Laser Interferometer Gravitational Wave Observatory. Picture 2 L-shaped detectors, one in Louisiana and one in Washington state, each with arms 2.5 miles long, measuring changes in length smaller than 1,000th the diameter of a proton. The detectors sensed ripples in spacetime itself produced by 2 black holes, 29 and 36 solar masses, spiraling together and merging 3 billion light-years away. The collision released 3 solar masses of energy as gravitational waves in a fraction of a second, briefly outshining the entire visible universe. The signal, lasting only 0.2 seconds, matched Einstein's predictions from 1916 precisely. Rainer Weiss, Kip Thorne, and Barry Barish received the 2017 Nobel Prize. Since then, LIGO and its European counterpart Virgo have detected dozens more mergers of black holes and neutron stars. To think that we can feel the vibrations of colliding black holes shaking the very fabric of space. The interstellar object Oumuamua was discovered on October 19, 2017, passing through our solar system. Imagine an elongated object at least 300 feet long but only 100 feet wide, tumbling end over end every 7.3 hours. Traveling at 196,000 miles per hour relative to the Sun. Robert Wyrick spotted it using the Pan-STARRS telescope in Hawaii, and astronomers worldwide rushed to observe it before it left the solar system forever. Its orbit proved it originated from interstellar space, not gravitationally bound to our Sun, the first confirmed visitor from another star system. Oumuamua showed no visible coma of gas and dust like a comet, yet it accelerated slightly as it rounded the Sun, as if pushed by outgassing to faint to sea. Its high reflectivity, elongated shape, and unusual acceleration sparked speculation ranging from a nitrogen iceberg to an alien probe, though most astronomers favor natural explanations. To think that we live in a galaxy where worlds and fragments drift between the stars, and occasionally one passes close enough for us to notice. The first image of a black hole's event horizon was captured in April 2019 by the Event Horizon Telescope collaboration. Picture 8 radio telescopes scattered across 4 continents, from Hawaii to Antarctica, synchronized to observe the same target simultaneously, effectively creating an Earth-sized telescope. The target was M87*, the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away and 6.5 billion times the Sun's mass. The image shows a bright ring of light from hot gas orbiting the black hole, with a dark central region where the event horizon blocks all light. The asymmetry in the ring's brightness comes from relativistic effects, as one side of the disk moves toward us and the other away. Processing the data required algorithms developed by Katie Booman and others, correlating petabytes of information recorded on hard drives flown between observatories. To think that we have photographed the unphotographable scene, the shadow cast by a region where space and time break down. Phosphine gas was detected in Venus's atmosphere in 2020, potentially indicating biological activity. Imagine Jane Greaves and her team using the James Clerk Maxwell telescope in Hawaii and the ALMA array in Chile, detecting spectral absorption lines consistent with phosphine at an altitude of 33 to 38 miles in Venus's clouds. On Earth, phosphine is produced mainly by anaerobic bacteria or industrial processes. No known abiotic process in Venus's atmosphere should produce it in detectable quantities. The discovery was controversial, with some teams questioning the detection and others proposing alternative chemical pathways that might produce phosphine without life. Follow-up observations have yielded conflicting results. If confirmed and truly unexplainable by chemistry alone, it could suggest microorganisms floating in Venus's temperate cloud layer, far above the hellish surface. To think that life might thrive in the clouds of the solar system's hottest planet, a possibility no one seriously considered until recently. The James Webb Space Telescope launched on December 25, 2021, beginning a new era in infrared astronomy. Picture a telescope mirror 21 feet across, segmented into 18 gold-coated beryllium hexagons, unfolding in space like a flower, along with a tennis court-sized sunshield to keep it cold enough to detect faint infrared light from the universe's first galaxies. Webb orbits the Sun-Earth L2 Lagrange point, about 1 million miles from Earth, where the combined gravity of Earth and Sun keeps it in stable position. Its infrared vision pierces dust clouds where stars are born, analyzes exoplanet atmospheres for signs of habitability, and looks back to when the universe was only a few 100 million years old. Early images revealed galaxies that formed far earlier than expected, challenging models of cosmic evolution. To think that we have placed in space a telescope sensitive enough to detect the heat of a bumblebee at the distance of the moon. Galaxies more massive and mature than expected have been discovered by the James Webb Space Telescope in the early universe. Imagine galaxies shining when the universe was only 300 to 500 million years old, yet already containing billions of stars arranged in disks and bars. Structures that should have taken much longer to form according to existing models. Some of these early galaxies appear as massive as the Milky Way, which seems impossible given the limited time available for stars to form and galaxies to assemble. The discoveries challenge theories of how quickly hydrogen and helium from the Big Bang could cool, collapse, ignite into stars, and organize into galaxies. Astronomers are revising models of star formation, efficiency, and dark matter behavior in the early universe. To think that the infant universe was far busier and more sophisticated than anyone predicted. That galaxies grew up faster than we thought possible. Exoplanets in the habitable zone with potential biosignatures have been identified through transmission spectroscopy. Consider K218b, a planet 8.6 times Earth's mass, orbiting a red dwarf star 120 light-years away, where JWST detected dimethyl sulfide in its atmosphere in 2023, a gas produced by life on Earth, primarily by ocean phytoplankton. The planet receives similar amounts of energy from its star as Earth does from the Sun, though it likely has a hydrogen-rich atmosphere, making it a Hycean world with a global ocean beneath a hydrogen envelope. Other observations have detected water vapor, methane, and carbon dioxide. The dimethyl sulfide detection is tentative and controversial, but if confirmed, it would represent the first potential sign of life beyond our solar system. To think that we might detect alien biology not by visiting other worlds, but by analyzing starlight filtered through their atmospheres. The planet Mars has 2 distinct hemispheres with dramatically different elevations, a mystery known as the crustal dichotomy. Imagine the northern third of Mars lying about 3 miles lower than the southern highlands, creating the most dramatic elevation difference of any planet in the solar system relative to its size. The lowlands are smooth and sparsely cratered, while the southern highlands are ancient and heavily cratered, suggesting the north is geologically younger. Scientists discovered this dichotomy through telescopic observations in the 1800s and confirmed it with spacecraft data. Theories for its origin include a giant impact from an object 1/10 Mars's mass in the first 100 million years of the solar system, or ancient plate tectonics that ceased billions of ago. Some researchers propose internal convection patterns created the asymmetry from within. To think that half a planet could be reshaped by violence so ancient we can only guess at its cause. The Great Attractor is a gravitational anomaly pulling our galaxy and thousands of others toward a region 150 to 250 million light-years away. Picture the Milky Way moving through space at 370 miles per second toward a point in the constellation. Triangulum Australe, drawn by the gravity of something massive hidden behind the dusty plane of our own galaxy. Alan Dressler and colleagues discovered this phenomenon in 1986 while mapping galaxy velocities in the local universe. The Great Attractor itself appears to be part of an even larger structure called the Laniakea supercluster, a collection of 100,000 galaxies spanning 520 million light-years. At the center lies the Norma cluster, dense with galaxies but obscured by the zone of avoidance where the Milky Way's dust blocks our view. We are falling toward this region and will continue falling for billions of years, though we will never arrive before dark energy tears the universe apart. This reminds us that even galaxies are not islands but swimmers in vast currents of gravity. Titan's lakes of liquid methane were confirmed by the Cassini spacecraft in 2007 when radar detected smooth surfaces indicating liquids. Imagine lakes near Titan's North Pole, some as large as Earth's Great Lakes, filled not with water but with liquid methane and ethane at temperatures of -179 degrees Celsius. The largest Kraken mare covers 154,000 square miles, larger than the Caspian Sea. Ligeia Mare is about as large as Lake Michigan. Radar measurements show these lakes are up to 560 feet deep, with transparent liquid allowing the radar to penetrate and measure the bottom composition. Seasonal changes occur as Titan orbits Saturn every 16 Earth years, with liquid evaporating from summer hemisphere and raining in the winter hemisphere Small waves, just millimeters high, have been detected on Ligeia Mare. To think that alien seas lap against alien shores on a frozen moon, that another world has maritime geography mapped with radar. The oldest known star in the universe, HD 140,283 or Methuselah, appears to be 14.5 billion years old, with an uncertainty of 0.8 billion years. Picture a star just 190 light-years away in the constellation Libra, composed almost entirely of hydrogen and helium with only trace amounts of heavier elements, indicating it formed when the universe was very young. The problem: the universe itself is only 13.8 billion years old, according to measurements of the cosmic microwave background. This created a paradox when the star's age was first calculated in the early 2000s. Refined measurements of its distance, brightness, and composition have brought the age estimate down, and with error bars, it is now barely compatible with the universe's age. The star likely formed within the first few 100 million years after the Big Bang from nearly pristine primordial gas. To think that we can see in our cosmic neighborhood a star that witnessed the universe's infancy, older than all the galaxies we observe in deep space images. Hypervelocity stars were discovered in 2005, traveling fast enough to escape the Milky Way's gravity. Imagine stars moving at speeds exceeding 1,000 kilometers per second, more than twice the escape velocity needed to leave our galaxy forever. Warren Brown and colleagues at the Harvard-Smithsonian Center for Astrophysics found the first one, SSJ 0907 45 0 tambah 024 1507, a star traveling. These stars likely gained their speed through gravitational interactions with the supermassive black hole at the galaxy's center, where a binary star system ventured too close, and one star was captured while the other was flung outward at tremendous velocity. Others may have been ejected during collisions between the Milky Way and smaller satellite galaxies. About 20 hypervelocity stars have been confirmed, all heading toward intergalactic space, where they will spend eternity in the void between galaxies. This reminds us that even stars can be exiled, cast out from their home galaxy to wander the cosmic desert alone. Methane lakes on Titan evaporate and leave behind deposits called evaporites, similar to salt flats on Earth. Picture the Cassini spacecraft's final close flyby of Titan in April 2017. Using radar to study small lakes in the Moon's southern hemisphere, some showed bright radar returns from their centers, indicating rough surfaces where something had precipitated out as the methane evaporated. On Earth, salt lakes leave behind flat deposits of minerals when they dry up, creating features like Utah's Bonneville salt flats. On Titan, organic compounds and possibly frozen benzene or acetylene settle out as the methane evaporates, creating raised deposits that may be porous, like a sponge. These evaporites could preserve organic chemistry from when the lakes were full, creating a record of Titan's chemical evolution. To think that an alien moon has features analogous to Earth's driest deserts, created by the same process but with entirely different substances. The cosmic web structure of the universe was mapped through galaxy surveys beginning in the 1980s. Imagine the universe not as a uniform distribution of galaxies, but as a sponge-like network with galaxies strung along vast filaments separated by enormous voids. The CFA Redshift survey in 1986 revealed the first large-scale structures, including the Great Wall, a sheet of galaxies 500 million light-years long, 200 million light-years wide, and only 15 million light-years thick. Later surveys like the Sloan Digital Sky survey mapped millions of galaxies, revealing that filaments connect at nodes where massive galaxy clusters reside, while voids hundreds of millions of light-years across contain almost no galaxies. Dark matter gravitationally shaped this structure over billions of years, with normal matter falling into the denser regions. Simulations of cosmic evolution accurately reproduce the observed web when dark matter is included. To think that galaxies trace out the invisible scaffolding of dark matter like lights, outlining a vast architectural frame. The Fermi bubbles are enormous structures extending 25,000 light-years above and below the Milky Way's center. Picture two hourglass-shaped regions of high-energy gamma rays discovered in 2010 by Doug Finkbeiner and colleagues analyzing data from the Fermi Gamma Ray Space Telescope. Each bubble spans about 50 degrees of the sky, roughly the width of 100 full moons. They were invisible until researchers processed the data to remove foreground gamma ray emission. The bubbles likely formed from a massive burst of energy from the supermassive black hole at our galaxy's core, perhaps 6 to 9 million years ago, when it consumed a large amount of gas or stars. Shock waves and cosmic rays propagating outward created the bubble's sharp edges. The entire structure contains as much energy as 100,000 supernova. This reminds us that our galaxy's central black hole, now relatively quiet, was recently far more active, and its outbursts reshaped the surrounding space on scales visible across the galaxy. The first repeating fast radio burst, FRB 121.102, was discovered in 2012 and traced to a dwarf galaxy 3 billion light-years away. Imagine a flash of radio, energy lasting just milliseconds but releasing as much energy as the sun emits in 10,000 years, then repeating irregularly over months and years. Most fast radio bursts occur once and never repeat, making them nearly impossible to study in detail. FRB 121.102's repetition allowed astronomers to precisely locate its origin in a star-forming region of a small galaxy. The bursts show no predictable pattern, sometimes occurring dozens of times in an hour, then remaining silent for months. Theories range from magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, to something entirely unknown. In 2020, a burst from a magnetar in our own galaxy was detected, strongly supporting the magnetar hypothesis for at least some fast radio bursts. To think that across billions of light years, something screams briefly in radio waves with the power of a sun's lifetime concentrated into an eye blink. Proxima Centauri b was discovered in 2016, orbiting the closest star to our solar system. Picture a planet at least 1.3 times Earth's mass orbiting Proxima Centauri, a red dwarf just 4.24 light-years away, every 11.2 days at a distance of 4.6 million miles. This places it in the star's habitable zone, where liquid water could exist on its surface despite the star's dimness. However, Proxima Centauri is a flare star, frequently erupting with radiation and charged particles that would strip away any atmosphere unless the planet has a strong magnetic field. The planet may be tidally locked with one side always facing its star, creating a permanent day side and night side. In 2020, a possible second planet, Proxima c, was detected farther out. The nearest potentially habitable planet orbits the nearest star, yet reaching it with current technology would take tens of thousands of years. To think that we might have a neighbor world but cannot visit it. That proximity in cosmic terms still means unimaginable distance. Tabby's star, KIC 8,462,852, showed irregular dimming patterns that defied explanation when discovered in 2015. Imagine a star 1,470 light-years away in Cygnus that dims by up to 22% at irregular intervals, far more than any known planet could cause. Tabitha Boyajian and citizen scientists analyzing Kepler space telescope data found the anomalous dimming events occurred weeks or months apart with no periodicity. Speculation ranged from swarms of comets to alien megastructures harvesting stellar energy, though astronomers emphasized natural explanations were far more likely. Subsequent observations showed the dimming was more pronounced in blue light than red, ruling out opaque objects like planets or structures and pointing to dust clouds. The star has dimmed by about 16% over the past century based on archival photographic plates. The leading theory involves disrupted comets or planetesimals creating variable dust clouds. To think that one star's odd behavior sparked speculation about extraterrestrial engineering, showing how little we still understand about stellar systems. The most distant galaxy confirmed as of 2023, JADES GSC 1320, formed just 325 million years after the Big Bang. Picture the James Webb Space Telescope peering back through 13.5 billion years of cosmic expansion to see a galaxy shining when the universe was only 2% of its current age. The galaxy appears as a tiny red smudge, its light stretched into infrared wavelengths by the expansion of space itself. Spectroscopy confirmed its distance through the redshift of its hydrogen emission line, measuring Z equals 13.2. meaning the universe has expanded by a factor of 14.2 since this light began its journey. The galaxy likely contains hundreds of millions of stars packed into a region much smaller than the Milky Way. Such early galaxies challenge models of how quickly the first stars could form from primordial gas. To think that we receive light that traveled longer than Earth has existed, that photons from the universe's childhood reach our eyes tonight. Betelgeuse's dramatic dimming in late 2019 and early 2020 worried astronomers that the red supergiant might explode. Imagine a star that normally ranks among the 10 brightest in Earth's sky suddenly fading to less than half its usual brightness by February 2020. Betelgeuse, about 550 light-years away in Orion, is a dying star near the end of its life, and such stars can explode as supernova with little warning. Analysis eventually showed the dimming resulted from a massive eruption that ejected gas from the star's surface, which then cooled and condensed into dust, partially obscuring the star from our view. The dust cloud dissipated, and Betelgeuse returned to normal brightness by mid-2020. The star has since dimmed slightly, again in its irregular pulsation cycle. When Betelgeuse does explode, it will briefly shine as bright as the half-moon and be visible in daylight, but we cannot predict when this will occur. This reminds us that stars die violently, and we watch them in their final breaths, knowing the detonation could happen tonight or in 100,000 years. The Oumuamua controversy regarding its acceleration continued through 2023 as scientists debated whether outgassing or some other mechanism caused it. Consider that an object showing no visible coma or tail still accelerated as if pushed by sublimating ice, behaving like a comet without looking like one. One team proposed in 2023 that trapped hydrogen ice, formed in dense molecular clouds and able to survive for millions of years, could outgas without producing visible jets, explaining both the acceleration and lack of coma. Others suggested radiation pressure from sunlight on an unusually low-density object could account for the motion. The possibility that Oumuamua might be an alien probe, while unlikely, cannot be definitively ruled out without more data. Abraham Loeb at Harvard has argued for keeping an open mind about artificial origins, while most astronomers insist on exhausting natural explanations first. To think that one object passing through has sparked such fierce debate about what counts as reasonable speculation versus wishful thinking about extraterrestrial technology. Volcanic activity on Venus was confirmed as recent in 2023 through analysis of Magellan radar images from the 1990s. Picture Robert Herrick and Scott Hensley discovering changes in a volcanic vent near Mahat Mongs by comparing images taken 8 months apart in 1991. The vent grew from 0.8 square miles to 1.5 square miles and changed shape, indicating fresh lava had filled it between observations. For decades, scientists knew Venus should be volcanically active due to its size and heat, but proof of recent eruptions remained elusive. The surface temperature of 465 degrees Celsius and atmospheric pressure 90 times Earth's makes studying Venus extraordinarily difficult. This discovery confirmed that Venus is geologically alive today, not frozen in ancient history. Volcanism may continuously replenish the carbon dioxide atmosphere, maintaining the runaway greenhouse effect. To think that under crushing heat and pressure, volcanoes erupt on our sister world, unseen and unstudied, reshaping a surface that melts lead. Quasar J03 Maret Taund 18 discovered in 2021 is the most distant quasar known, existing when the universe was only 670 million years old. Imagine a supermassive black hole containing 1.6 billion times the Sun's mass, shining with the luminosity of a trillion suns when the first galaxies were still forming. Feige Wong and colleagues found it in data from multiple telescopes, including the Magellan Observatory and Gemini North. The black hole's immense mass, so early in cosmic history, poses a severe problem for theories of black hole formation and growth. Standard models predict such black holes could not have grown so massive so quickly from stellar mass black hole seeds. Astronomers have proposed direct collapse black holes forming from massive gas clouds that never form stars, creating black holes of thousands of solar masses immediately. This quasar suggests the early universe was far more extreme than previously thought. To think that black holes billions of times the sun's mass existed when the universe was in its infancy. That monsters lurked in the cosmic nursery. The Parker Solar Probe became the first spacecraft to touch the sun's atmosphere in 2021, passing through the corona. Picture a spacecraft protected by a 4.5-inch thick carbon composite shield, diving to within 6.2 million miles of the sun's surface, where temperatures reach millions of degrees, but the thin gas delivers relatively little heat to the spacecraft. The probe measured the precise point where the solar wind becomes supersonic and can no longer return to the sun, a boundary called the Alphen critical surface. On April 28, 2021, Parker Solar Probe crossed this boundary, entering the corona, where magnetic fields dominate plasma behavior. The spacecraft discovered magnetic switchbacks, kinks in the magnetic field shaped like letter S, that may help accelerate the solar wind. Future passes will bring it even closer, to within 3.8 million miles. To think that we have built something that survives the sun's outer atmosphere, that we can sample the fires that feed the solar system. Atmospheric rivers on Saturn's moon Titan were identified in 2022 through modeling of Cassini data. Imagine massive flows of methane vapor moving through Titan's atmosphere, analogous to atmospheric rivers on Earth that transport moisture from tropics to higher latitudes. These features likely drive much of Titan's hydrological cycle, moving methane from Titan's equatorial region toward the poles where it rains into the lakes and seas. The rivers in the sky aren't visible but are inferred from temperature and composition measurements, combined with atmospheric circulation models. They may be responsible for creating Titan's asymmetric distribution of surface liquids, with most lakes concentrated in the North Polar region. Seasonal changes as Titan orbits Saturn probably shift these atmospheric patterns, creating multi-year cycles of evaporation and precipitation. To think that another world has weather patterns fundamentally similar to Earth's, despite operating at temperatures where methane takes the place of water. That the physics of fluid transport creates familiar structures from alien substances. The first planet discovered around another star using the transit method was HD 209458b in 1999 by David Charbonneau and colleagues. Picture a team pointing a modest 10-centimeter telescope at a star 150 light-years away, measuring its brightness as a planet passed across its face, dimming the star by 1.5% for 3 hours. This hot Jupiter, orbiting every 3-5 days, had already been detected through radial velocity measurements. But the transit confirmed its existence and allowed measurement of its size, about 1.4 times Jupiter's diameter. The transit method proved so successful that NASA's Kepler Space Telescope used it to discover thousands of exoplanets by continuously monitoring over 150,000 stars for years. Kepler found that planets are common, with most stars hosting at least one planet, and small rocky planets are more numerous than gas giants. To think that a technique watching for tiny dips in starlight has revealed that we live in a galaxy teeming with worlds. The WOW signal detected on August 15, 1977, remains the strongest candidate for an extraterrestrial radio transmission. Imagine Jerry Emmon reviewing computer printouts from the Big Ear Radio Telescope at Ohio State University, seeing a signal intensity of 6 EQUJ5 in the data, where 5 represented the strongest possible reading on the scale used. The signal lasted 72 seconds, exactly matching the window during which the telescope's beam would sweep past a point source as Earth rotates. The signal came from the direction of Sagittarius. was narrowband centered at 1420 MHz near the hydrogen line, and has never repeated despite dozens of subsequent searches of the same region. No known natural source produces such signals, and no human-made transmitter could match it from that direction. Explanations range from a one-time transmission from an extraterrestrial civilization to a passing comet's hydrogen cloud to unknown terrestrial interference. To think that for 72 seconds in 1977, something caught our attention so strongly that nearly 50 years later we still wonder what it was. Rogue planets, not gravitationally bound to any star, were discovered floating freely through the Milky Way. Imagine worlds ejected from their birth solar systems through gravitational interactions with other planets or passing stars, cast into interstellar space to wander the galaxy alone in eternal darkness. The first strong evidence came from microlensing surveys in the 2000s, where a foreground planet's gravity briefly magnifies light from a distant background star. Calculations suggest there may be billions of rogue planets in the Milky Way, possibly outnumbering stars. Some may retain moons that could harbor life warmed by tidal heating rather than starlight. In 2021, astronomers discovered OGLE 2016 BLG 1928, a rogue planet between Mars and Earth in mass, proving that even small rocky worlds roam between the stars. These orphan worlds experience perpetual night at temperatures just above absolute zero. To think that planets can exist without suns, that worlds wander the galaxy's dark spaces, and that one could drift through our solar system unnoticed unless we happened to look exactly the right direction. The Hubble constant tension refers to measurements of the universe's expansion rate that disagree depending on the method used. Picture cosmologists measuring expansion through observations of the cosmic microwave background radiation, finding a rate of about 67 kilometers per second per megaparsec, meaning galaxies 1 megaparsec away recede at 67 kilometers per second. Meanwhile, observations of Cepheid variables and supernova in relatively nearby galaxies yield about 73 kilometers per second per megaparsec. This 9% discrepancy might seem small, but both methods are precise enough that the disagreement is statistically significant and has persisted through years of refinement. Either systematic errors affect one or both measurements, or our cosmological model is incomplete and something about dark energy, dark matter, or cosmic evolution is not yet understood. The James Webb Space Telescope has confirmed the higher value through independent distance measurements. To think that we cannot agree on how fast the universe expands, that this fundamental number remains uncertain, suggesting something profound missing from our understanding. Europa Clipper, launching in October 2024, will perform 49 close flybys of Jupiter's moon Europa to investigate its subsurface ocean. Imagine a spacecraft the size of a basketball court carrying ice-penetrating radar, magnetometers, spectrometers, and cameras to study the ice shell's thickness, the ocean's depth and salinity, and the composition of surface materials. The mission will search for active plumes like those on Enceladus, and if found, will fly through them to sample ocean material directly. Radiation from Jupiter's magnetosphere makes Europa's surface one of the harshest environments in the solar system, receiving doses that would kill a human in hours. So the spacecraft will orbit Jupiter and make brief dips past Europa rather than orbiting the Moon directly. The mission aims to determine if Europa has conditions suitable for life, paving the way for a future lander or submarine probe. To think that we will soon map an alien ocean from above, measuring its depth through miles of ice, searching for signs that it might shelter living things in its dark waters. The first Earth-sized exoplanet in a habitable zone, Kepler-186f, was discovered in 2014, orbiting a red dwarf star 500 light-years away. Picture a world just 10% larger than Earth, receiving 1/3 the energy our planet gets from the Sun, making it potentially cool enough for liquid water if it has a substantial atmosphere. Elisa Quintana and the Kepler team detected it through the transit method, watching it cross its star's face every 130 days. Kepler-186f orbits near the outer edge of the habitable zone where temperatures would be similar to Mars without greenhouse warming, but a thick carbon dioxide atmosphere could warm it sufficiently. The planet's star is an M-dwarf, cooler and dimmer than our Sun, meaning the planet would receive mostly red and infrared light, potentially affecting photosynthesis if plant-like life exists there. Red dwarf stars live trillions of years, far longer than Sun-like stars, giving life immense time to develop if it arises. To think that an Earth-sized world orbits in another star's habitable zone, that somewhere in Cygnus, a planet might harbor conditions for life as we know it. The asteroid Bennu was found to be ejecting particles from its surface when visited by NASA's OSIRIS-REx spacecraft in 2019. Imagine a spacecraft approaching a small asteroid only 1,600 feet across, expecting a quiet rubble pile, instead witnessing dozens of particle ejection events over months of observation. Some particles escaped into space, while others orbited Bennu briefly before falling back to the surface. The ejections occurred most frequently in the late afternoon on Bennu's surface, suggesting thermal stress as the primary cause, where rapid temperature changes crack rocks and release particles at speeds up to 7 miles per hour. Other possible mechanisms include meteoroid impacts, too small to see directly, and water vapor release from hydrated minerals. Bennu's surface proved far more rugged than expected, covered in boulders rather than smooth regolith, forcing mission controllers to target a much smaller landing site than planned. To think that even small asteroids are dynamic worlds, where rocks crack and particles leap into space from heating and cooling. The galactic center's supermassive black hole, Sagittarius A*, was imaged by the Event Horizon Telescope in 2022, revealing its shadow. Picture a black hole containing 4.1 million solar masses, around which hot gas orbits at a significant fraction of light speed, completing circuits in just minutes. The resulting image shows a bright ring of emission with a dark central shadow, similar to the M87* image but harder to capture because material orbits so rapidly that the structure changes during observation. 8 radio telescopes observed simultaneously on the night of April 6th to 7th, 2017, and teams spent 5 years processing the data and developing algorithms to reconstruct the image from rapidly varying signals. The shadow's size matches predictions from general relativity precisely, measuring about 52 microseconds across, roughly the size a donut on the moon would appear from Earth. The black hole sits 26,000 light-years away at the galaxy's heart. This reminds us that the still point around which our entire galaxy rotates is a region where space-time curves so steeply that nothing returns. Phosphorus, essential for life as we know it, was discovered in molecular clouds where stars form, traced through the molecule PN. Imagine astronomers using the ALMA telescope array in Chile to detect phosphorus monoxide in star-forming regions in 2016, showing that this crucial element for DNA, RNA, and cell membranes exists in the interstellar medium and gets incorporated into new planetary systems. Victor Ravilla and colleagues found PN in the molecular cloud surrounding a young star system in the constellation Ophiuchus. Later observations detected it in Comet 67P Churyumov of Gerasimenko, suggesting comets may have delivered phosphorus to early Earth. The discovery traced a pathway from interstellar clouds to comets to planets, demonstrating how life's ingredients circulate through the cosmos. Phosphorus is created only in massive stars and scattered through supernova explosions, making it relatively rare. To think that atoms of phosphorus in your DNA were forged in dying stars, drifted in dark clouds, and arrived on Earth aboard ancient comets. The most massive neutron star ever measured, PSRJ 0.74 Tamba Numribu Numratas Duopula, was found in 2019 to contain 2.14 solar mass. Picture a sphere just 15 miles across containing more than twice the Sun's mass, spinning 346 times per second, sending out pulses of radio waves with the regularity of an atomic clock. Emmanuel Fonseca and colleagues measured its mass using Shapiro delay, observing how the neutron star's gravity warps space-time and delays the arrival of pulses when its white dwarf companion passes between us and the pulsar. This mass approaches the theoretical maximum for neutron stars, beyond which nothing can prevent collapse into a black hole. The limit likely falls between 2 and 2.5 solar masses, depending on the exact properties of matter at nuclear densities. Finding such massive neutron stars helps physicists understand the behavior of matter crushed beyond atomic nuclei into pure neutrons. To think that there exists a maximum density for matter, that beyond a certain point, not even neutron degeneracy pressure can resist gravity's pull. Amino acids were discovered in samples returned from asteroid Ryugu by Japan's Hayabusa 2 mission in 2020. Imagine opening a sealed capsule containing 5 grams of pristine asteroid material, never contaminated by Earth's biosphere, and finding more than 20 different amino acids, including several not commonly found in Earth organisms. The asteroid material was analyzed in vacuum chambers with extraordinary contamination controls, and the amino acid isotopic ratios proved they formed in space, not on Earth. Ryugu is a carbonaceous asteroid, rich in carbon compounds and water-bearing minerals, representing the type of object that bombarded early Earth. These discoveries support the hypothesis that some of life's building blocks arrived from space rather than forming in Earth's oceans. The asteroid samples also contained uracil, a nucleobase used in RNA. To think that asteroids carry the chemical ingredients for life, that we are partly made of matter delivered by ancient impacts, that life's recipe was written in space before Earth fully formed. Saturn's rings are much younger than the planet itself, possibly forming only 10 to 100 million years ago. Picture the Cassini spacecraft's final orbits in 2017, diving repeatedly between Saturn and its rings, measuring how much material falls from the rings onto the planet. The results showed rings losing mass rapidly, suggesting they cannot be as old as Saturn's 4.5 billion years. The rings contain mostly water ice, with only small amounts of rocky material and organic compounds, unlike the mix expected if they formed with Saturn. The leading theory proposes that a small, icy moon or large comet strayed too close to Saturn within the last 100 million years, and was torn apart by tidal forces, its fragments spreading into the magnificent ring system we see today. If correct, humans are lucky to exist during the brief cosmic moment when Saturn wears its spectacular rings. To think that these rings, Saturn's defining feature, might be temporary jewelry, that in 100 million more years they could rain away, leaving a bare planet. Water geysers on Europa were observed by the Hubble Space Telescope in 2012 and 2016, erupting from the Moon's southern hemisphere. Imagine plumes of water vapor reaching 125 miles above Europa's icy surface, offering potential access to the subsurface ocean without drilling through miles of ice. Lorenz Roth detected the plumes using ultraviolet spectroscopy, observing hydrogen and oxygen signatures as Europa passed in front of Jupiter. The plumes appear intermittently and may be controlled by tidal stresses that open cracks in the ice when Europa is farthest from Jupiter in its slightly elliptical orbit. Unlike Enceladus's continuous geysers, Europa's plumes seem sporadic and harder to predict. A spacecraft flying through these plumes could sample ocean water directly, analyzing it for organic molecules, salts, and potentially biosignatures without landing. The Galileo spacecraft may have passed through a plume unknowingly in 1997, recording a brief magnetic field anomaly. This reminds us that moons sometimes exhale their secrets, that patient observation reveals doors to hidden oceans. The Chicxulub impactor that killed the dinosaurs 66 million years ago was identified as a carbonaceous chondrite asteroid in 2021. Picture Mario Fish GGD analyzing the osmium isotope ratios in sediments from the Cretaceous-Speleogene boundary, finding signatures matching primitive carbonaceous chondrite meteorites rather than other asteroid types or comets. The impactor measured roughly 6 miles across and struck the Yucatan Peninsula with energy, equivalent to 100 trillion tons of TNT, creating a crater 110 miles wide and throwing enough debris into the atmosphere to block sunlight for years. The impact triggered global wildfires, acid rain, and climate change that eliminated 3/4 of Earth's species. Carbonaceous chondrites, rich in carbon and water, represent some of the most primitive matter in the solar system. Many such asteroids orbit in the outer asteroid belt. To think that a single rock from beyond Mars reshaped life on Earth forever. That all mammals' age began with a stone falling from space. Ancient Mars was much wetter than previously thought. According to analysis of the Geran rover's data published in 2022, imagine China's rover examining rocks in Utopia Planitia, finding hydrated minerals and features suggesting substantial liquid water existed in that region between 1.5 and 2.8 billion years ago, far more recently than the wet period thought to have ended 3 billion years ago. The rover detected evidence of past flooding and sedimentary layering consistent with water flow and pooling. Some scientists propose Mars experienced multiple wet periods rather than a single early wet era followed by permanent drying. The implications suggest Mars remained potentially habitable more recently than assumed, giving life more time to develop if it ever arose. The planet's loss of its magnetic field and subsequent atmospheric stripping by solar wind gradually reduced surface water, but pockets may have persisted in isolated regions. To think that Mars's habitability may have extended billions of years longer than we believed, that the window for Martian life to emerge and evolve may have stayed open into relatively recent geological time. The largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, spans roughly 10 billion light-years. Picture a concentration of gamma-ray bursts detected in a region so vast it challenges the cosmological principle that the universe should appear uniform at large scales. Istvan Horvath and colleagues identified this structure in 2013 by mapping gamma-ray bursts which mark distant galaxy clusters and trace large-scale structure. The wall's existence at such scale seems to violate predictions that structures larger than 1.2 billion light-years should not form. Light takes 10 billion years to cross this structure, meaning we see different parts of it as they existed at vastly different cosmic times. Some cosmologists question whether this represents a true single structure or a chance alignment of smaller structures along our line of sight. To think that the universe contains features so large they strain our theories of how cosmic structure forms, that uniformity at the largest scales may be more assumption than observation. Betelgeuse has a companion star, discovered through analysis of its velocity variations in 2024. Imagine the red supergiant, hundreds of millions of miles across and massive enough that its core will soon collapse into a black hole, paired with an unseen companion orbiting every 2,170 days. The companion likely formed from the same molecular cloud as Betelgeuse and has orbited it for millions of years, possibly influencing the supergiant's evolution and contributing to its unusual asymmetric appearance and mass loss. The companion has not been directly observed because it is vastly outshone by Betelgeuse itself, detectable only through subtle Doppler shifts in Betelgeuse's spectrum as both stars orbit their common center of mass. When Betelgeuse explodes, the companion may be ejected at high speed to become a hypervelocity star, or it might be destroyed entirely by the supernova blast wave. To think that even famous stars hide companions, that nothing in space is truly alone, that Betelgeuse's spectacular death will be a binary event. Dimorphos, a moonlet orbiting the asteroid Didymos, was deliberately struck by NASA's DART spacecraft on September 26, 2022, in humanity's first asteroid deflection test. Picture a 1,210-pound spacecraft traveling at 14,000 miles per hour deliberately crashing into a 560-foot-wide asteroid moon to change its orbit. The impact shortened Dimorphos's orbital period around Didymos by 33 minutes, far more than the minimum 73 seconds needed to declare success. The collision excavated a crater and ejected enough material to form a temporary tail thousands of miles long, visible from Earth-based telescopes. Follow-up observations by the European Space Agency's Hera mission will arrive in 2026 to study the impact site in detail. The test proved that kinetic impactors can deflect asteroids,